Today in class, you simplified rational expressions, and today we're going to talk about rational functions, which are the ratio of polynomial functions. So basically a polynomial in the numerator, polynomial in the denominator. Okay? And then we'll continue with operations on rational expressions. So today we're going to start with an example of a function f of x equals x plus 6 divided by the quantity x minus 3. Okay, and we're going to talk about some of the characteristics as well as do some problem solving. So first we're going to algebraically determine the y-intercept, and then we'll also check it graphically. So the y-intercept is where it intersects the y-axis, which means that x equals 0. So we're going to evaluate our function at a value of x equals 0. Okay, so we have 0 plus 6 divided by 0 minus 3, which is 6 over negative 3, or 2. So we have the point 0, 2, which means it intersects the y-axis at 2. Okay, now we'll do the same thing, algebraically determine the x-intercept of this function. Okay, and so the x-intercept is where y equals 0. So we're solving y equals x plus 6 over x minus 3, or 0 is equal to x plus 6 over x minus 3. Well, how do we get a function to equal 0? We said we can't have 0 in the denominator because that would make it undefined. So technically we're worrying about where the numerator is equal to 0. So 0 would have to be in the numerator to have an answer of 0. So you're solving x plus 6 equals 0, or x equals negative 6. Okay, and then we'll be able to take a look at the graph in a moment to see that that is in fact the x-intercept. Okay, now the next question, letter C, has to do with undefined, and we spent time talking about undefined today during class, yesterday for homework when we were doing our station activity. What value of x would make this function undefined? So what makes things, or fractions specifically, undefined? When our denominator is equal to 0. So that means we would have our denominator set equal to 0. So x equals 3 is a value where this function is undefined. Now in just a moment we're going to take a look graphically, and what happens at x equals 3 is that you get something called an asymptote. And in this case we have a vertical asymptote, and an asymptote is a line that the graph approaches but kind of veers off away from it in either direction, and doesn't touch the asymptote. Although once you get to pre-calc, we will talk about sometimes graphs do touch the asymptotes for low values of x, but we're usually concerned about what happens at the ends of the graph, talking about limits. And okay, so now we'll take a look at that last question, D, which says, based on our answer for C, state the domain of this function. So basically the domain means values of x that would work in the function. So pretty much any value of x would work in this function except denominator were equal to 0, so x equals 3. So how do we write in interval notation everything except 3? That means everything from negative infinity to 3 exclusive, with everything from 3 to infinity. Okay, all right, let's take a look graphically. So on the graphing calculator, I've typed in f of x equals x plus 6 over x minus 3, and we have this somewhat unusual looking function. This is a rational function, and we can see that our, whoops, I forgot my negative on my paper here, we can see that our y-intercept is -2, as we found algebraically. We can see that our x-intercept here is -6, as we found algebraically. We could also confirm and check that x-intercept we could do, and the y-intercept, we could check them using the table. We could also check them by analyzing the graph. I'm going to take a look at the table because Control T, remember, gets us a table. The nice thing about the table, as we can see, 0, -2. Okay, I'm going to go down to my, -6. I can see -6, 0, so that confirms my x-intercept. But you'll notice at 3, it shows us hashtag, essentially, UN, meaning undefined. So it's saying at 3, we have undefined value. Okay, so that's a nice thing that it's telling you, hey, this is where the asymptote is. Okay. Control T, remember, will get rid of your table. And I'm going to just take a moment to analyze the graph. I'm going to graph trace, actually. And when I do graph trace, I can enter a value for x, and we were going to look at x equals 3. Okay? When I type in x equals 3, you'll notice the graph, on the graph appears a dotted line, and that's usually how we represent an asymptote, with a dotted line. And then it says 3 undefined. So it warns you or tells you, yep, that's the undefined value. So it kind of confirms what we found algebraically. Okay, and then that can help you to determine your domain. So it looks like every x value works except as we get close to that 3 value. Okay, I'm going to ask you to complete exercise 2 and exercise 3. You can either pause the video now and complete those, or complete them after we do the last problem on the next page. You're going to find all values for which this function is undefined, okay, and then you can verify using the graphing calculator. So essentially, we're only looking for where the denominator is equal to 0. So you will set this denominator equal to 0. How do we solve these? We factor. If it's not factorable, then we would go ahead and use one of the other methods for solving quadratics, quadratic formula, or completing the square. However, this one is factorable because we have 2 times -6, which is -12, and we need 2 factors of -12 that add up to +11. Okay. Then I'm going to ask you to complete number 3, which asks you to find the domain. So in order to determine the domain, you need to find where is this undefined. Once you know where it's undefined, then you can go ahead and determine what the domain is based on that information. Okay. And then, of course, we will go ahead and check that one and this one graphically in class tomorrow. Okay, and then on the back, example 4 is a review question. It's asking you whether or not this rational function is even or odd. Okay, determine which it is algebraically, and then we'll talk about what kind of symmetry it would have if it's even, or what kind of symmetry it would have if it's odd. So just a reminder, in order to show even or odd, we have to evaluate f of -x. Okay, so if we evaluate f of -x, we have -x, the quantity squared, minus 8, over 4 times -x. Okay, so that means we have in the numerator x squared minus 8 over -4x. Okay. All right, so given that information, we have to decide, is this even, is this odd, is it neither? Okay, and how do we go about doing that? So we have to remind ourselves, if f of -x is equal to the original function, then we have an even function. If f of -x is equal to negative of the function, then we have an odd function. Okay, so I'd like you to just take a moment to consider those two and decide, what do you think? Do you think this is even based on what we have? Do you think that this is odd? Okay, so it looks like it's definitely not even, right? It's not exactly the same. So we have to decide, is this the same as negative of the function? Okay, so just a reminder that if you have, like, let's say negative 1/2, that's the same as 1 over negative 2, which is the same as negative 1/2 if we're talking, regular fractions. So does this negative indicate that the whole function is negative? Okay. And so, I mean, could we pull this negative out here? Could we divide it into the numerator and have it over 4x? Is that the same thing? And I would say yes. So we would say that this is an odd function. And we'll go ahead and look at it graphically. Okay, here's the graph of this function. And remember, if it's an odd function, it's symmetrical with respect to the origin, meaning it's the same as a rotation of 180. So if I look at the graph upside down, does it look exactly the same? And it does. So we have confirmation of odd function. Okay, tomorrow during class we'll work on the problem set. Remember, tonight I'd like you to finish up exercise 2 and exercise 3. See y'all tomorrow.